Ya, investigación sobre el tiempo, veo un libro en línea.
Necesito hacer un paseíto por allí, por la universidad. ¿No es una nueva registro de intenso?
Me va a pasar.
No, yo tengo un deseo muy grande.
Hello, welcome. It's a privilege for me to introduce you Professor Laurent Drissen. He comes from Canada. He got his master's degree and PhD thesis in Montreal University, where he was working on the properties of world-radiate stars. Then he spent 5 years as a postdoc in the Space Telescope Science Institute in Baltimore, working on several topics in astronomy, before coming back to Québec, this time to Laval University, where he's working now. And at this stage, he started his interest on instrumentation for astronomy. In particular, he has developed two imaging Fourier
transform
spectrometers, yes, sorry. So, which are very interesting instruments. The first one was a small prototype spion for the Mont Mégantic Observatory, and the second one is SITELLE for the Canada-France Hawaii telescope. And I have to say that he was awarded a prize from the Canadian government for his role in the construction of this instrument. And well, he's explaining us about this instrument and all the possibilities to get good science from this. So thank you very much.
Muchas gracias, Jorge. So my talk will be very superficial. So I will not go into details because the main purpose is to introduce you to SITELLE, to the instrument, and to some of the science that can be done. And also my second purpose is to talk to you about the relationship that we developed between Granada and Quebec. So, oops. Okay, so this is Quebec. Of course, this is Granada. And I came here with my wife, Carmel, who is also an astronomer, and she works on massive stars. She couldn't come here today, but she also works with me à la Universidad. So this is Quebec, so we can have a kind of a Alhambra, también. But it's a hotel for rich people, so we never go there, and it was built only 100 years ago. But yeah, there's a kind of a relationship. So the main reason why we are here is that we started a collaboration a few years ago with Salvador Duarte Puertas, who was a postdoc at our institute, and he did his PhD here in Canada. And it's a real collaboration between Canadian universities and the institutes here, the University and also. And it's by far the largest PI program that was developed for SITELLE. We have another program, and I will talk to you about it later, but it was like a legacy program. But this is by far the largest PI program with SITELLE. And the goal was to essentially detect and characterize the intergalactic H2 regions in the Hickson compact group of galaxies. This is what I will do. I will talk to you about some of the projects we have, and I will talk to you about SITELLE, and then I will talk to you about other projects I have. So we go from one project to the other, from redshift 0 to redshift 0.35, something like this. So SITELLE, and I will come back later to explain to you how it works and what it is exactly, but SITELLE is an imaging Fourier transform spectrometer. So it's essentially an IFU with a field of view of 11 by 11 arc minutes. And it works in the visible band, essentially from 350 to 850 nanometers. And the natural units, because you will see spectra that are like reversed. The left will be on the right and the right will be on the left, because the natural units of an FTS are wave numbers, right? It's not wavelength, it's wave numbers. And it took me about 10 years to get used to it. So now I see, for example, in the spectrum, I see the sulfur 2 lines to the left of H alpha. But I mean, you can get used to it too. So I will come back to explain what SITELLE is and how it works. So the project actually started when Salva was still a student with Pepe and Jorge, and he came to our institute to work on one of the first data cubes that we had obtained with SITELLE in 2015, which was one of the Hickson compact group, which is the Stephan's quintet. And so two papers came out of this collaboration. And here is, for example, it's a deep frame coming from SITELLE. And we discovered a new galaxy. So it's not Stephan's quintet anymore. It's Salva's sextet. So it's this galaxy here, and this is the velocity map of this. So what we have, I'm really sorry for these things. I tried to remove them, but I mean, it's the technology. So we have 6 Hickson compact groups that we have observed with SITELLE. A 7th might come in the next year. So we have 2 fields, for example, in Hickson 16. 1 in 31. We had 3 fields in Hickson 44 and 68 and 93. So we have data cubes in the red around H alpha with a resolution of 3000. Marie, salut. I did not expect to see Marie here. The last time we saw each other was in Ouagadougou. Okay. So resolution of 3000 in the red and a resolution of 1000 around H beta and also in oxygen 23727. I will talk to you about the first target that we decided to work on while we are here. Of course, in our list of things to do, because we are here only for 2 months, October, November, and we had a list of things to do. We are on sabbatical. Carmel and I are on sabbatical. You know, a list of to-do things. We were supposed to work on all of them, but we decided that one was enough. So Hickson 31 is the first one that we have observed. It's at 51 megaparsec. So all that I will show you is just work in progress. I will just show you a few slides of the results. So this is the entire field of SITELLE. It's 11 arc minutes by 11 arc minutes. I focus on the region where we found H2 regions. Obviously in the main galaxies, but we also found H2 regions outside of the main galaxies, which was the main purpose of this project. The first thing I did when we arrived here is to compare the result because Muse had observed Hickson 31 a few years ago. The paper was published in 2023. We just wanted to make sure that we have more or less the same results as Muse. So this is SITELLE. This is the log of the equivalent width in H alpha, and this is what Muse had. Muse, the field of view of Muse is 1 by 1 arc minute, and so they had, I think, 3 or 4 fields for Hickson 31. So this is only the central part that we have, and this is where we found H2 regions from this galaxy here to the small, completely isolated, and there is no any obvious there is no obvious continuum around here. So these are H2 regions. These are the regions we were looking for. So this represents about 20% of the field of view of SITELLE. This is the heliocentric velocity, and this is an example of an H alpha line that has been found for one of these H2 regions. This is the galaxy here. It's a small galaxy, so we have maps of different line ratio, but I just show you the equivalent width, the heliocentric velocity, and the velocity dispersion here. Actually, to measure the velocity dispersion, as I will show you later, is one of the advantages to have a Fourier transform spectrometer, because the line shape is different from the line shape of a standard spectrometer. So the precision we can have on the velocity dispersion is higher for the same spectral resolution. And since the field of view is so large, we also have galaxies in the background. And these are just a few examples of galaxies where we found in this SN3 filter that I will show you around H alpha, we found a few galaxies at redshift of 0.36 all over the field. This is another example. So here we have H beta and oxygen 3, and here we have just oxygen 3. So yeah, the strongest line is to the left. As I told you, it took me about 10 years to get used to it. Okay, the second paper we will work on is, actually we will talk about this, I hope, later today, is a paper about an interacting duo of galaxies, ARP-143, that we observed with SITELLE. So this is the velocity map, but we had added to that simulations made by the first author, Hugo Martel, here. So we have essentially 4 million dark matter particles and particles of gas. We include hydrodynamics, radiative cooling, star formation, feedback. I will show you a map later with the feedback, metal enrichment, and metal diffusion that we include in that. And if you have an instrument that provides you 4 million spectra, and you add it to some simulations, the papers are just huge and gigantic. So a few things that can be done, and this was work with between Carmel and Salva, the metallicity. So it's very strange because this has been an interacting galaxy. So the gradient is very, very strange. There's a lot of dispersion around the median, but it's normal for this kind of galaxies. And we also used the Dragonfly telescope array. These are a series of relatively small lenses by Canon that are added together to reach essentially very low magnitude limit, very low surface brightness limit. And I don't know if you can see it from here, but we see like a blue tail. It may not be obvious on the screen, but it's more obvious here on my computer. And in this part here, this was observed with SITELLE, and this is the SITELLE image. And we found a few H2 regions in the tail, and they are, I mean, it's not visible, but it's about 5 times the Orion Nebula. So these are very faint. Well, this is kinematics around the nucleus, and we found some evidence for either outflow or inflow on both sides of the nucleus. And these are the results of the simulation enlarged. What we see here is the age of the stars going from 0 to essentially 500 million years. And what we notice, for example, in the gas, the blue points that we have here is gas that has been created in the past 100 million years or so. So this is feedback from the stars. There is no evidence for an AGN here. So here it's mostly the feedback from the stars, so massive stars, winds, and supernova as well. So this was chapter 0. I have way too much slides, okay? I have 90 something slides, so I will not go over all of them, obviously. So at some point I will have to stop, but since I'm going from one topic to the other, it has no importance. So I prepared just a very brief technical introduction to SITELLE, what it is. Then I will talk about supernova remnants in the Milky Way, the Crab Nebula and Cassiopeia, and some supernova remnants outside the Milky Way. So SITELLE is installed at the Canada-France-Hawaii telescope, which is at 4,200 meters. And this is snow. It's like the Sierra Nevada. We have snow, and this picture was taken when Camille and I were in Hawaii for our last sabbatical in 2017. It was strange to have snow in Hawaii before they had snow in Quebec City, which is kind of strange, but it's the way it works. And when there is snow in Hawaii, it's like, 30, 50 centimeters of snow at the same time. So the telescope looks like that. And I was in Colorado yesterday, and the two telescopes are, big telescopes built in the 1970s, 1980s. So the diameter is 3.6 meter. Focal ratio is F8, so it's very similar to Colorado. And SITELLE is right here. I don't know if you can see it, but it's right here. So it was built in Quebec City. It's a collaboration between Université Laval, ABB, the Canada-France-Hawaii Telescope, University of Hawaii, and Université de Montréal. So again, the field of view, 11 by 11 arc minutes. The sampling is 0.32 arc seconds, so we use CCDs as detectors, and we have two CCDs. I will explain later. We work in the visible band, 350 to 850 spectral resolution. In the lab, we could go up to about 40,000, but of course, you need photons to do that. So we've been able to reach 15,000 in terms of resolution, and I will show some of the results. So we use filters. The SN1, 2, and 3 are to sample the strong lines. So the Balmer lines, oxygen 2, oxygen 3, nitrogen 2, and sulfur 2. So I don't know if you can understand the words, but I mean, it's quite obvious that it's kind of strange because instead of using a dispersive element, we use a Michelson interferometer. I don't know if you're familiar with Michelsons, but you put a Michelson on a table in a lab, and there is a bit of wind or people walk, and then everything moves and you don't have fringes anymore. So our main challenge was to put a Michelson in an instrument, in a telescope where, you know what happens to the telescope. There is wind, the temperature changes. The telescope, in Mégantic, it does make noise. In Canal Alto, it doesn't make noise, but at Mégantic, it makes noise and brrr, like that. So the main challenge was to make sure that the two mirrors on the Michelson were aligned to within about 10 nanometers. So, I mean, I could go into details for the next 2 hours, but I will not do it. So we have built a prototype. This is our telescope in Quebec. It's about 3 hours drive from Laval University. So it's a 1.6 meter telescope, and this is Espion, the prototype. And actually, you remember going to the observatory? Jorge came to the observatory at the beginning. So, and we spent a few nights observing. So when we showed that it could work, then we got a grant to build SITELLE. So what it is, it's essentially an imager at the core of which you add a Michelson interferometer. And we have a metrology with laser, and 10,000 times per second, we measure the distance between the two mirrors and the angle between them. 10,000 times per second, but we do not correct at 10 kilohertz, we correct at something like 50 hertz. But we have to measure it at a higher pace to make sure that we don't miss anything. So this is the key technological challenge that we had to overcome. So the way it works, we take a series of images, and in between these images, we move the mirror. So the light path between the two arms of the Michelson change as a function of time. So this is an example, it's N51, obviously. Can you see the fringes, the contrast between the fringes? So we move the mirror like that. And for each point, you record the intensity at each pixel. And it looks like this. This is an interferogram. In this case, I mean, the background has changed, or this is a pure raw data. So we have 1 interferogram per pixel. So that's 4 million interferograms. And then we take the Fourier transform to get the spectrum. So if we focus on that, so in normal Michelson, half of the light goes back to the source. We don't want that, right? We want 100% of the flux to be analyzed. So the Michelson is kind of off center. We enter with an angle so we can separate the two outputs. So we have 2 cameras, and you see the fringes. The fringes here are mainly from the night sky, the OH lines around H alpha. And it may not be obvious on the large images, but if we focus here, we see that we have destructive fringe here and 2 constructive fringes here. And for the other camera, it's the opposite. So what you have on one camera, on one end of the Michelson, is like the complementary interferogram of the other. And it will be more obvious in the next slide. So this is it's a group of pixels integrated for one camera in blue, the other camera in red, and I will enlarge it. So you see when the signal is lower here, it's higher here. So when you add the two, you have 100% of the flux. How do you get a spectrum? Well, you take the Fourier transform, and you get that. This is H alpha N2, the sulfur 2. And you see here the kind of side lobes that we have. This is not noise. It's part of the instrument line shape of a Michelson. And the reason for that is just that we start observing at some point, we end observing at some point. So it's like a square like that. When you take the Fourier transform of a boxcar function, then you have a sinc function. So this is what we have here. So when you take the sum of all interferograms, you have a deep frame. And you can do whatever you want with the deep frames. Like this is the ratio of the two data cubes. But when you take the Fourier transform, then you can get the spectrum, you can get the velocity and the line ratios and everything. So it's like a paradigm shift between using a dispersive element and using an interferometer. So it has advantages and disadvantages, of course. It's not a miracle. Some of the advantages is that the field of view can be huge, like 11 by 11 arc minutes. At the beginning, I said in my dream case, I had 20 or 25 arc minutes on the side, but the people who did the design, the optical design, said, no. 10 minutes is the most that you can get. We got 11 arc minutes. So the field of view is large. The global transmission is very high as well. You have a lot of flexibility in terms of spectral resolution. You can decide to have a spectrum with a resolution of 3000 or 5264 if you wish. It's very, you can change it anytime you want. We lose things. We have a smaller simultaneous spectral coverage. And the reason for that, this is why we use filters, it's because of the distributed noise, right? Because what we do, for example, when you take a spectrum with a standard dispersive element, the noise that you have at a given wavelength is the square root of the number of photons you have at that wavelength, right? But for an FTS, you take images and you just change the distance between the two mirrors. So you take images, so the noise that you have, the square root of the total number of photons in the band. So this is why I didn't mention it, but the last E in SITELLE is for emission. So it's a perfect instrument to do emission line studies. It's less advantageous to do absorption and continuum. So there's a kind of observational niche for this kind of instrument. So I will go through a few examples of the science that has been done. This is a resolution of 2, so it's essentially a deep frame. And this was part of a study to study Markarian 266. So it's like a deep field, if you wish. So we can go for a resolution of 1 or 2. A resolution, well, it's not, I don't want to remove it, otherwise everything will break. But the resolution was 15,000. So we have used a narrow filter that encompassed only H alpha and nitrogen 2. And we used it essentially like in Fabry-Perot to get a resolution of 15,000. And this is NGC 2903, beautiful spiral galaxy. You can separate the two nitrogen lines from H alpha very easily. And we get very good values of the velocity dispersion. So I will go from one extreme to the other. In the blue, we go down to 350 nanometers. For example, one thing that I really wanted SITELLE to do is to get the oxygen 23727 emission line. So this is a map of an irregular galaxy, NGC 4449. We've done Orion. We've been able to separate the two lines from the doublet. You can do some absorption. So SITELLE is not optimized to do absorption, but we can do it. So these are the high order Balmer lines for this nucleus of M33. So this is in the blue, and in the red, we can go up to 850 nanometers. This is an example of a study that has been done on a cluster with a redshift of around 0.24 to get H alpha at that redshift. So we use the filter, which is called C4. And they have been able to show that in some cases, the H alpha, well, the gas there is some gas stripping that the galaxies are going inside the cluster, and there is some kind of gas stripping. This has been done also for the Virgo cluster galaxies by people in Marseille. Alessandro Boseghi has done it for a local cluster. And I added that because I know that someone from here has worked at a redshift of 0.5 or something. Isabelle Marquez? No? Anyway, I just wanted to show what she has done with the cluster. Okay, chapter 2. If you want, I can come back. Since I'm very close from here, I just take the tram. For those of you who are interested in more technical aspects of this instrument, I can come back and explain more, like give a small course. Supernova remnants in the Milky Way. I am not an expert on supernova remnants, but these are extremely interesting objects to study, and I really love to use SITELLE to work on that. So I work with experts, and essentially the two experts here are Dani Milisavljevic from Indiana University and Tia Timon from Princeton. So we've been working together in the Milky Way, in some objects in the Milky Way, and it's a collaboration between the James Webb Space Telescope and SITELLE. And Salva is here because Salva has also worked on supernova remnants, and some of my other students here. So again, it's a SITELLE James Webb collaboration. And it's strange because these objects are really bright, right? M1 is a Messier object. And still in 2025, there is still something to learn about Messier objects. As I mentioned, I'm also an amateur astronomer. So it's a picture I took of the Crab Nebula when Mars was very close to it. No telescope, just my camera with a 135 millimeter lens. So this is the paper that has been written on the James Webb. This is a James Webb image. So the Crab Nebula, we know exactly its age. The diameter is 3 parsec. There's only 5 solar masses of gas. And people are still looking for gas, but the gas and dust, but the most we found was 5 solar masses. The expansion velocity is around 1,500 kilometers per second. So we did a first study with SITELLE in 2000. We took a spectrum in 2016, a data cube in 2016, and this is essentially what we have, a spectrum. And I show this just for pedagogical purposes. I will show you a data cube before the Fourier transform. So this is a raw data cube. I will show you a cube after the Fourier transform, so you can see the difference. So we will go through the different steps in the data cube before the Fourier transform. So these are interferograms, right, at different points. So region 1 is here, 2, 4, etc. So we see how strange this can be. And we will just go up to here because something happens here, which is very interesting. At this point here, the 2 mirrors are exactly at the same distance from the beam splitter, the Michelson. And you will see that what will happen. It's coming soon. Boom. And then the fringes go the other way around. So I will stop here. And now when we take the Fourier transform, then we have a spectrum for each pixel. And what you see here, again, this is the sulfur 2 doublet is here. What you see are multiple components along the line of sight. Here it's H alpha, nitrogen 2, and sulfur 2. So this is a strong sulfur 2 at some places. And then you have almost nothing for a few minutes, and I will stop here. But you see the difference between the original data cube and after you take the Fourier transform. So this would be, for example, the kind of cube that you get with any kind of imaging spectrograph, like PMAS, for example. And from that, we could get a 3D version of the Crab Nebula. And actually, you can get inside and get to see one filament and get the line ratios, get the density, and so on. It's extremely rich, so the data have not been completely analyzed. I will start that because it lasts for some time. We took another data cube in 2022. The data cube was much deeper. The quality was much better. So this is an image with H alpha, nitrogen 2, and sulfur 2 in different colors. So it's very deep. But what's interesting is that the Crab Nebula is so young that just between 6 years, you can see the tangential velocity as well. So we took two different slices at exactly the same velocity. And so this is 2016. And this is 2022. You probably saw it moving. So it means that we really have the 3D velocity for each point of the nebula. So it's work in progress. But what we conclude from the data that we have so far is that there is some evidence from the velocity map that first the shape is kind of it's like a heart. It's very strange, and there is evidence for some kind of deceleration shortly after the explosion by the circumstellar material that has been blown away by the star prior to the supernova. Another one, Cassiopeia. Its age is about 345 years. There is no conclusive evidence for any observation at that time. Some people say that Flamsteed has observed it. It's not clear. It's not, historians of science are not convinced that it is the case. The diameter is about 2 parsecs, and the expansion velocity is very high. It's around 5,000 kilometers per second. So this is an HST image. So we do not have any evidence for people seeing it, but we do have an excellent spectrum. I don't know if you are aware of this. This is one of the most mind-blowing papers I've read in astronomy. And I don't know if you have a slide. No, I don't have a slide, but it's echo. So the light coming from the supernova has reached some regions in the Milky Way where it has been reflected towards us. And so there was a spectrum of one of these echoes that had been obtained a few years ago. So we do have a good spectrum of the supernova. So we know what kind of supernova it is, and we can refer to models. And so the mass of the progenitor is around 15 to 20 solar masses. We have observed it a long time ago with Espion, the SITELLE prototype, and we have made the first 3D version of this nebula. So we observed it with SITELLE in 2024 with a spectral resolution of 4,000. So again, the field of view is 11 by 11 arc minutes. So these are very preliminary results. This is the heliocentric velocity. These are examples of some spectra. So the velocity, for example, the reference velocity of the two sulfur lines is supposed to be around here. And we have some extremes here at around 3,000 to 4,000 kilometers per second. And you see that even in one component, you have a different, very strange velocity dispersion pattern. Since we have the data cube from Espion from 2009 and the data cube from SITELLE from 2024, I will show you the difference. So again, with a velocity of an ejection velocity of 5,000 kilometers per second, you can see the tangential movement. You will notice also a difference in image quality. So this is 2009, exactly the same velocity slice, 2009 with Espion, and 2024 with SITELLE. So from 2009 to 2024. So again, we see the movement like that. We can do the same with, for example, an image that was obtained with HST in 2004. So this is HST, and this is SITELLE. So you see the evolution in the tangential velocity, and we have, of course, a velocity in line of sight velocity in 2009 and another one in 2024. So again, we will have the 3D velocities. This is the velocity dispersion. But what interests me in that, I will leave the supernova remnants for the specialist in the team. What interests me is what we call the QSF. It's completely masked by this thing. The quasi-stationary flocculi in Cassiopeia are pieces of material that have been ejected by the star before the explosion. This is why they are called quasi-stationary flocculi. The velocity is just a few hundred kilometers per second, and they are very strong in nitrogen too. And I don't know if you can see the green contours here from the supernova remnant itself, but here are the QSF. And so this is a velocity map of the QSF. This is the nitrogen 26584 map. The histogram of the pixel velocity, so you see that it does not go as fast as the supernova remnant itself. It's just a few hundred kilometers per second, centered on the velocity of the object. So I will show you just a few examples of the QSF spectra. This is one. So the size here is 0.21 parsec, and this is the velocity dispersion. So if you take a spectrum of this region, for example, this is the spectrum you have. So again, nitrogen 2 is much stronger than H alpha, but you see the velocity structure is very complex here. You have at least two components, two velocity components, and this is the kind of study that we're doing. Here's another example. So we have the flux in nitrogen 2, heliocentric velocity. So within a single QSF, you have difference in velocities. Let's say about 80 kilometers per second difference. This is the velocity error. So in the core, we are below 1 kilometer per second of uncertainty. Velocity dispersion and an N2 over H alpha ratio. Here's another example. So these are probably two different QSFs with different velocities. Again, there's a large scatter and nitrogen 2 over H alpha ratio as well. I have until 15, right? 2 more minutes. Good. And I can stop anytime. So I will talk a bit about signals. So it's a large program that was awarded 55 nights at the CFHT with SITELLE to study 30 galaxies. So this is Pierre Martin, Carmel, Laurie Housson-Lepton, and myself. With these are the resolution that we've used: 5,000 around H alpha and 1,000 around oxygen 3 and oxygen 2. So we have a sample of local galaxies. Excuse me. Some more galaxies. So we have spirals. We have irregular galaxies. Yeah, this is NGC 6822, and this is Zelinda, which is a solar system object. And these are some of the fields that we have for local group galaxies. This is N33, N31, IC 1615, and NGC 6822. There are many ways that you can find supernova remnants in external galaxies. The ones that we use are I mean, it's certainly not complete because there are other criteria to find supernova remnants. We use line ratio of sulfur 2 of H alpha larger than 0.4 and a velocity dispersion larger than about 25 kilometers per second. Again, this is one of the ways that we can find the supernova remnants just by looking at the velocity dispersion. And as I mentioned before, when there is no velocity dispersion along the line of sight, the instrumental line shape of a Fourier transform spectrometer is a sinc function. It's like that. So, for example, this is an H2 region with essentially no velocity dispersion, 14 kilometers per second. And you can see the line shape, you can see the side lobes of the sink. When you increase the velocity dispersion of this case, it's 26 kilometers per second, then you convolve the instrument line shape with a Gaussian, for example. And so you see that the side lobes are not as strong as when there is no velocity dispersion. And then when you increase to 50 kilometers per second, then the line shape is dominated by the Gaussian from the extension of the object. And deconvolving this kind of shape from a sinc function is much easier than to deconvolve two Gaussians. And this is why SITELLE can get pretty good measurement of velocity dispersion. So again, with Salva, when Salva Duarte Puertas was with us as a postdoc, he arrived at the beginning of the pandemic. It was awful for him to move in Quebec in 2020 when the pandemic was, anyway, he was brave. So we looked at some targets, NGC 6822 and M33. And for example, this is the only supernova remnant in this galaxy, Hodge 12. So we could measure the velocity dispersion for each of the knots. This is very strange supernova remnants with different knots. We actually invented a parameter which is called Xi, and it's the multiplication of the S over H alpha ratio times the velocity dispersion, which actually can separate pretty well the supernova remnants, as we see here, from the H2 regions. So we've seen M33 again, and I will not go through the 163 objects that we have analyzed, but this is an example. This is the H alpha map, the sulfur 2 over 8 H alpha. It's very strong. It's over 0.8 velocity dispersion, and this is the spectrum. And this is what we call the diagnostic diagram for it. Since it's already there, the only thing I want to mention now at the end, I just missed a few slides anyway. If you have been interested in some of the science that I've shown, the next call for proposal at CFHT is in March. And it will be the last, because SITELLE will be decommissioned from CFHT in February of 2027. So if any one of you is interested in working with SITELLE, the CFHT is extremely well open to collaboration, international collaboration. The PI can be from Spain. The only condition is that you must have Canadian or French collaborators, but CFHT is really open to the community. So if you're interested, just contact me. And I will be very happy to help you with writing the proposal and eventually designing the project if you wish. And this is a picture of the comet Lemon. I don't know if you are aware of this comet, but I took this picture from my balcony in an apartment which is close to the university. So light pollution was everywhere, and just with my simple camera, and this is just 30 times 1 second exposure. So from the countryside or from Canada, it must have been a very good sight. So thank you very much.
That time for questions, comments.
That's wonderful talk.
Thank you.
For your book, and especially SITELLE. So how sensitive is SITELLE to very faint light emission lines? Very faint.
Okay, so we can reach in 3.5 hours, we can reach about 3 times 10 to minus 17 with the SM3 filter. So it really depends on the kind of filter and lines that you, but it's around that, a few times 10 to the minus 17.
And can you elaborate? I'm guessing you have worked on wavelengths or some of your past work.
Yes.
So can you mention a bit on that?
Oxygen 343,
Yeah.
63, for example.
For example?
We have done that, yes, for NGC 6888. Do I have it here? I can show it afterwards if you wish.
Yeah.
So NGC 6888 is Wolf-Rayet Nebula,
Mhm.
and yeah, 4363 was visible in very narrow filaments all over the place. We also have the nitrogen 25755, also in the same nebula, and I know that it has been done also for bright objects. So I wouldn't go to diffuse ionized gas, for example, in external galaxies and get these lines. Although, I mean,
Yeah.
if you want, why not? A good proposal can be written for that.
Very nice talk and impressive results. I wonder whether you've been able to identify sources in the observation of nearby galaxies that could be associated with nova remnants.
Yes, unpublished data on M31. We have actually observed nova and nova remnants. Mike Shara was interested in finding them, so he sent me an email 7 years ago.
Did you
So-
reply?
Yes, I did reply. Mike Shara was my supervisor when I was a postdoc in Baltimore, and the data are public, and actually we found lots of them. We looked at the nova from the beginning of the century, and we found nova remnants. Yes, the data are public, and Mike has done so many other things that if you're interested, then the data cubes are yours. Yeah, I'm serious. I'm really serious. Yes, and so we've looked at M31. We haven't looked specifically for other galaxies, but this can be done. I remember the work in M31 because we have a list.
Yeah,
But pretty-
they should show us point sources with a large dispersion in the velocity, I guess.
Enrique?
Yes, very impressive talk, Laurent. Congratulations. I'm very sad not to be able to see most of the images you have shown, because I remember 10 years ago when Laurent was here, that showed some images from SITELLE. For me, that I'm blind, I cannot see them, and now and probably they are very impressive. But my question is about, you commented that the dispersion is different when you're measuring emission lines or you're measuring the continuum absorption lines. Is this a drawback when you try to subtract the underlying continuum in some galaxies when you have both the ionized gas and the very prominent all the stellar population? Is this a problem of overall when you're trying to get these emission lines, these objects?
Actually, Carmel, who is not here today, she actually has a program to do that. So yes, what we do is we select pixels in the data cubes that show no emission, but show absorption. We combine them. We actually put them at the same velocity because, of course, you have velocity gradient across the galaxies, and combine them and then we go through PPXF to get a model, and we subtract the absorption line that we see from the data cube. So we can't actually subtract the absorption, especially at H beta. In H alpha, the difference is not that large, but at H beta, it can play a role, and it can of course affect the value of the absorption that you get from the Balmer line ratios. Yes, and actually the SN1 continuum, the region around oxygen 2 is very rich in high order Balmer lines, and we use that, and it's really helpful to constrain the model with PPXF of the stellar population and to subtract it from the spectrum. Also, you met Loki.
Yes, she was here some years ago, yeah.
Yes, yes, yes.
Yeah,
She's the PI of
yeah,
Signals.
yeah.
Or questions?
Thank you, Laurent. Impressive. So I have just a question because you mentioned that when you were deconvolving the profile, the line profile with the interferometry, with respect to the classical diffraction spectrograph which are Gaussian, you have mentioned that it's more sensitive to sigma, to the.
Yes.
Can you elaborate a bit more why this profile resolved better?
That's a question for Thomas Martin, who is actually the guy who worked on the analysis program. It's when you do the mathematics, which I don't have in mind now, but it's easier. And for example, I was a referee for a paper that was actually written by someone in Spain. I don't remember who she was. But she used spectra from Muse, data from Muse, with a resolution of 3000, which is not very different from the ones we have. And for her, it was very difficult to get a proper value of the velocity dispersion below 60 kilometers per second. Here we can go down, of course, it depends on the signal to noise, but we can go down to 10 kilometers per second with a resolution of 5000 because of that.
This is very interesting. So you are able to resolve the PSF in a different way. So it's oversampling the PSF with respect to classical Gaussian.
Yes.
Thank you.
And it's kind of it's disturbing when you go through the cube because close to the line you have pixels with a negative value. And you say, what's that? You have a data cube with negative values, but the negative values are actually part of the signal. And again, like it's difficult to get used to having the wavelength around, then having these side lobes. Now I feel so good when I see a spectrum with side lobes. So
You are sampling the
the line, yes.
Yeah.
Yeah, you mentioned, I think, 2 or 3 Hickson groups in your approach. I wanted to ask if you are there any in your database that you've already worked with?
Sorry.
Hickson groups.
Yes, the Hickson group.
Are there any others that you've targeted in your project? You mentioned 31, for example, in Stefan's group.
Yeah, so 16, 30, 31, 44, 68, 93.
So,
The next one will be 100 probably in the spring. And so we just have a small sample. So if you're interested in observing some of the Hickson contact groups, then please contact me. I would be very happy to answer.
yeah, the question about that was, do you have any criteria specific?
I'll do two specific examples. Well, I leave the expert. What shows what were groups that were quite early in the mixing and the encounter between the galaxies, and like 31, which is actually pretty well within the merging process. So we have 3 categories, and this is how we selected them.
Or, I mean, random question, but is it anywhere related to the?
No problem. That was not even.
At any stage, do you consider, for example, the gas content in neutral gas content in these places that you're talking about, stages?
We were looking at the H1 maps, right, to select them. Essentially, the H1. We haven't looked at the dust. No, but essentially comparing the H1 with the H2.
Yeah, but HCG 30 are advanced, so why was it selected?
Because they selected in 3 different stages.
Okay.
It's a sample.
To include all the state.
Does not pretend to be complete at all. It's just used for illustrating the face.
The CFHC didn't let us observe the 100.
Do you see any difference between the pages? No.
It's XM31 is the first,
Okay.
and that we are observing, and we see differences. We see obvious differences between the different Hickson groups that we have observed. But I mean, it's too early in the analysis to say anything about it.
More questions?
Out of the field. Has anyone tried to observe comets emission of comets, for instance?
I know that Jean-Pierre Maillard from Paris was very interested in doing that. We have not seen any proposal, but this can be done.
Yeah.
This can be done. The only thing,
It's
yeah, at the CFH, I know that you can guide on a moving target. That's very important for the microscope. You cannot observe an object which moves. So well, you could, but I mean, the software analysis would be very difficult. But it's certainly possible. Yes. And we have broadband filters as well. The data that I showed were obtained with narrowband filters, but we have C1, C2, C3, and C1 covers pretty much some of the interesting lines for comets. Yes. Molecular, the lines of molecules and.
Thank you.
More questions? I have actually one question myself. Do you know, just can you comment on the possibilities of the SITELLE images, the large field of view for cosmological projects? I mean, the outskirts of the. Do you know if someone has tried to discover, I don't know, Lyman alpha meters or?
Not specifically. We found a few Lyman alpha emitters in some of the field, but it was just by chance.
Nothing
So,
systematic.
Nothing systematic has been done. Not
It's
at all.
also another possibility.
Yes, of course. Yes. So, of course, in these narrowband filters, we find, I don't know, maybe a dozen background galaxies, but with the widest one, the C1, C2, C3, we can find many more.
More questions? Do we thank again?
Thank you.